The principles behind the detection of radiation using a gas proportional counter are presented in this module. You may want to use the module on interactions of radiation with matter as a reference with this module. The objectives of this module are listed on this slide. Several new terms are introduced in this module. You should be able to define or describe the following: voltage plateau, deadband, upper and lower level discriminator, crosstalk, and the importance of chemical separations when performing radionuclide specific analyses. The key concepts to be presented in this module specifically deal with the setup and calibration of the gas proportional counting instrument and the effect the positioning of discriminators and voltage settings will have on analytical accuracy. The distance that decay particles travel in matter is related to their charge and mass, and also the density of the matter that they are interacting with. For alpha and beta particles, the primary means of interactions are by ionization of atoms by removing a valence shell electron from the atom. Gamma rays interact by complete energy transfer in a single interaction with a K-shell electron. This too creates ion pairs, but at a much lower probability of interaction. The higher the charge on the particle, the larger will be the ionization per unit distance traveled. The higher the mass of the medium that makes up the detector, the larger the electron density is, and thus there will be a greater number of ionizations per linear path length of the particle. If we combine these two concepts, ionization capability and detector material density, we find that using a gas like argon as a detector will provide very good sensitivity to the ionization characteristics of alpha and beta particles and poorer response to gamma radiation. The picture to the right shows a primary ionization event when an alpha particle interacts with a neutral gas molecule. An alpha particle will expend its entire energy by tens of thousands of mechanisms just like this in a few centimeters of linear path length of argon gas. A beta particle will create ion pairs in a similar fashion except at a much lower rate. The number of ion pairs that these primary ionization events lead to can be used to distinguish between alpha and beta particles. Gas proportional counters have excellent sensitivity to low levels of alpha and beta radiation. These detectors can be used for general screening of samples or for radionuclide specific analysis. The table on the slide identifies several different methods that utilize gas proportional counting for these purposes. It is very important to recognize that if radionuclide specific analysis is to be performed, that chemical separations must be performed and must provide excellent separation from other radionuclides. This is because the gas proportional counter cannot discriminate between alpha particles of different energy or beta particles of different energy. It can, however, differentiate between alpha and beta particles. The resulting gas proportional counter output is total counts for alpha or beta. Some instruments have the capability to provide the user with spectral output of accumulated counts versus energy. However, due to sample self-attenuation for alpha emitters and the broad energy spectrum of beta particles, these spectral outputs can only provide very general information regarding the potential of radionuclide cross-contamination of the final sample test source that is counted. The diagram on the right shows a cutaway view of a basic gas proportional counter that has a thin window. This means that the sample is located outside the active detector area, in this case the flowing argon gas. The walls of the detector cell are the cathode and the central detection wire is the anode. If no voltage were applied across these two portions of the cell, and ionizing radiation caused an ion pair to form, the ion pairs would recombine because there is no driving force for them to separate. In this picture, we see the initial ion pair that is formed within the detector cell. However, here, a bias voltage has been impressed across the cell, and the ion pairs formed will separate and migrate to their respective electrode. The external circuitry of the instrument will allow charges to be collected for a certain migration time, and then cut off any additional charge collection. The total charge collected is temporarily stored in the electronic circuitry and called a pulse. The magnitude of this pulse, called the pulse height, is measured, and one count is stored in system memory in a broad region allocated to either alpha particles or beta particle response. The voltage gradient between the two electrodes will accelerate the ion pair towards their respective electrodes. If the electrons have sufficient kinetic energy, they can create additional ion pairs by collision with other gas atoms. Since the ionization of the first interactions will be multiplied, the total collected charge increases. The effect is known as the Townsend avalanche. The greater the number of primary events created by the original particle, the larger will be the total charge collected at the anode. Alpha particles create many more primary ionization events than do beta particles. Remember that this is due to the greater charge, greater energy, and also the short distance they travel before expending all of their energy. The extent of the Townsend avalanche is controlled by the bias voltage applied to the detector. As the voltage is increased above zero, up to about 400 volts, secondary ionization effects are minimal and the resultant pulse size is small. This region of the voltage curve is used for instruments called ionization chambers. If the voltage is increased to approximately 1500 volts, the Townsend avalanche creates so many subsequent ionizations after the initial events that there is no distinction in pulse height between alpha and beta particles. So what happens in between 400 volts and 1500 volts? In that mid-voltage range, the number of primary ionization events is directly proportional to the amplified pulse produced as a result of the Townsend avalanche. Thus, the final pulse height is proportional to the initial energy deposited in the gas proportional detector cell. One distinct advantage of counting in the proportional region of voltage is that the signal amplification factor distinguishes between alpha and beta particles, but the background count rate from lower voltages is not increased significantly. Thus, the signal-to-noise ratio, also referred to as the figure of merit, is increased. This makes detection of these particles more achievable at lower concentrations. As the voltage across the cell electrodes is increased from 0 volts, the first particle to create enough ion pairs to be detected will be an alpha particle. When the gas proportional counter is set up, one of the first functions is to find the voltage region where counting a sample will yield a constant count rate for a pure alpha particle source. In this region, beta particles do not create enough ion pairs to yield a measurable signal. The extent of this plateau is usually about 200 to 300 volts, and the slope of the curve is very flat in this region. The alpha operating voltage is set above the knee of this curve by approximately 50 to 100 volts. Beta particles ionize much fewer atoms per linear path length than do alpha particles. Thus, in order to accumulate enough collected charge for a measurable pulse, the amplification of the original beta particle ionizations need to be more significant than for alpha particles. Thus, there is a very limited beta contribution to the pulse size in the alpha region. However, if we increase the voltage, we can locate a similar plateau for beta particles as for alpha particles. The major differences are the more gradual knee until the plateau, and the rate of change on the plateau is slightly greater than for alpha particles at their plateau. Remember that any alphas that are present in the sample will also add to the count rate at the beta plateau. However, as long as the instrument has pulse height discrimination, we can differentiate most alpha from beta counts. Once the detection system has an applied voltage in the beta region, any alpha or beta particle that enters the detector chamber will result in a pulse. As we will see later, it is the size of that pulse that discriminates between the two different particles. Instrument setup is not calibration. Instrument setup establishes where the voltage regions are for counting alpha and beta particles. These regions may be very detector specific. Keep in mind that the detector system must be fully in operation when this function is performed. That includes the proper type and purity of counting gas and the flow rate that will be used to count the samples. The general steps of setup are identified on this slide. The picture on this slide shows the curve of count rate versus increasing voltage. Note that the left-hand side of the curve is starting at the end of the alpha plateau of 705 volts. The voltage curve slope is expressed as a percent of change in the slope. For a curve that is perfectly flat, this should be 0% across the plateau. Let's say, however, that you go from 1520 volts to 1620 volts, and the count rate increases from 20,000 to 20,200 counts. This would be a slope change of 1% per 100 volts. This is a good plateau region. If the instrument has only one voltage control for all the detectors, each detector's curve will need to be determined separately. Once that is determined, find the voltage region where the sum of the slopes for all detectors is at a minimum. The instrument setup establishes the operating conditions for the instrument to optimize its response. Calibration identifies how many counts the detector will record for a sample of known activity in disintegrations per second in a specific sample matrix and in a specific geometry with respect to the detector. We had noted earlier that the pulse size, that is, the height, generated by an alpha particle event is much larger than that generated by a beta particle event. Each event is a single count, and the height of the pulse obtained from each count is measured. We can distinguish between alpha and beta particles based on this height. First, the pulse is collected, and then it is assigned as an alpha or a beta count based on its height. The term sometimes still used for a spectrum of accumulated counts versus energy is pulse height analysis, or PHA. A sample containing both strontium-90 and plutonium-239 was counted on a gas proportional counting instrument that had pulse discrimination capability. The spectrum shown here are accumulated counts versus the pulse height. Remember, the pulse height is proportional to the particle energy. Alpha particles in general have higher energies, and thus we expect to find the peak for the alpha particle at the right-hand side of the spectrum. The alpha particle energy has a distinct maximum, with some amount of lower energy straggling. The beta peak, on the other hand, is relatively broad. This difference in peak shapes is due to alpha particles being monoergic and beta particles having a wide range of possible energies due to neutrino formation during the decay process. In this case, the beta spectrum also has the complicating factor that there are actually two different beta emitters present, strontium-90 and its ingrown progeny, yttrium-90. Using the previous spectrum as an example, if we can use the detection system electronics to determine if a signal is either above or below a certain value of pulse height, we can distinguish between alpha and beta particles. This determination is done with electronic filters known as discriminators. The instrument will have both high and low discriminators for both alpha and beta energy regions. A beta low energy discriminator may be set in some instruments to reduce background noise from the instrument. An alpha high energy discriminator can be set at the highest channel in the spectrum, ensuring we record all the pulses from alpha particles detected. As you can see on this slide, there is a region of pulse heights that is between alpha and beta particle responses. Depending upon the thickness of the sample and its average atomic number, there may be considerable confusion by the detector as to which pulse is an alpha or beta particle. After all, the detector is just discriminating the pulse height, not the particle itself. If the same sample has high-energy beta emitters, it may not be able to be significantly attenuated, and its pulse may show up in the low end of the alpha region. This phenomenon of the detection system being confused as to which particle has caused the pulse is called crosstalk. We want to ensure that we count all particles as correctly as possible, especially when performing gross alpha-beta analysis, since no chemical separations are done. The placement of the beta high and the alpha low discriminators should be based on knowledge of the samples being counted and the matrix that the radionuclides are presented in. This placement should maximize the counts that can be ascribed to the beta channel and minimize the number of crosstalk counts from alpha into beta. We can minimize the overlap of the counting regions by creating a deadband. This would require setting an upper beta discriminator at a significantly lower energy than is the highest energy beta expected to produce a signal, or by setting the lower alpha discriminator above the energy of the lowest alpha straggling energy. This situation is depicted in the picture on this slide. It is important to note that by doing this, that we will reduce the total number of counts accumulated in each window by changing the region of interest, which leads to losing counts into the deadband. When performing analysis close to the detection limits, this is not an ideal situation. There may be instances where sample count rates are much higher than background in well-characterized samples with known radionuclides. In these cases, the window can be minimized to achieve a more significant figure of merit than by opening up the window to the full width possible. Since most drinking water samples will have low levels of radioactivity, we want to be sure that we use all the counts that the detector sees. Ultimately, this will either reduce sample size or shorten counting time. Thus, in order to use all counts available, the analyst should configure the instrument to have no deadband. However, the drawback to not having a deadband is that the analyst will need to decide at what point in the energy spectrum the discriminators will be aligned so that it is equitable for all samples, and 2, the analyst will need to determine the crosstalk factor for gross alpha and beta samples of varying sample areal densities. Areal density means the milligram of sample residue measured in milligrams per square centimeter of planchette surface area. The overall checklist for instrument preparedness is: gas quality is appropriate, gas flow rate has been set and is constant, operating voltages for plateaus have been established, self-attenuation curves have been determined, crosstalk factors have been measured, quality control checks have been performed. Once all these tasks are completed and the information recorded in the appropriate quality assurance file, the system is now ready to be used for counting. None of these parameters should be changed. If they are, setup and calibration may need to be repeated and voltages and settings reestablished. There are several different gas proportional counting instrument manufacturers and several different versions even for individual manufacturers. It is imperative that you thoroughly review the operating manual for your system before making any adjustments or voltage settings. Some items to note are listed on this slide. Typically, gas proportional counting instruments utilize a combination of active and passive shielding to minimize background counts. Passive shielding is the lead that surrounds the detector chambers so that ambient radiation entering the chamber is minimized. However, cosmic radiation can penetrate the detector shielding and create ionizing events in the active detector area. If radioactive sources containing gamma rays are kept in the same room as the gas proportional counting instrument, they can also create background radiation through bremsstrahlung and Compton scattering that can elevate detector backgrounds. Active shielding combines electronics and additional detection devices to minimize background. Liquid scintillation counters used a technique to reduce background called coincidence counting. Due to the fact that all radiation events from the sample would cause floor molecules to emit scintilla of light in every direction, there was a high probability of these scintilla being detected simultaneously in the two detectors surrounding the liquid scintillation cell. This was termed coincidence counting since both detectors had to receive a scintilla in a short time frame for the count to be recorded. In a gas proportional counter, a guard detector may be installed with the instrument. All alpha and beta particles from decay of environmental radionuclides will be shielded from the sample detector by the passive lead shielding. However, cosmic radiation will penetrate the active guard detector and may cause random events in both the guard and the sample detectors. When this occurs, the system is set up to discard those counts as not being from the sample. This is referred to as anti-coincidence, since when counts are recorded simultaneously in both detectors, the counts are not recorded. One of the first tasks to perform after instrument setup and calibration is to determine background count rates for all the individual cells. Not only is this going to be used for correcting for gross activity to net activity, but it will also be used to assess the stability of the instrument. A background count time that is much longer than normally expected sample count times can be used to assess both activity and uncertainty. Using a longer background count time will generally decrease the uncertainty contribution to the final activity concentration. However, it should be used with caution since backgrounds can vary slightly over short counting intervals. Although shorter count times may lead to larger uncertainty, they also provide for better sample throughput. Thus, routine checks of both long and short background counts should be performed. Longer background checks are generally performed at a lower frequency than the background count times that match the sample count times. When the count times for the samples and the background are the same, they are called paired. The total detected activity and energy of both alpha and beta particles are diminished by the fact that most samples have some mass to them. There are certain sources that are considered massless. These are usually electroplated standards. Regardless of the types of sources that are available, the calibration of the sample self-absorption curve must be performed with solids that will closely match the average Z value of the samples to be measured. Self-absorption curves are prepared by taking solutions of varying solids content. The solids should be of the same salt and have the same known amount of radioactivity added to each solution. The range of solids usually varies from about 5 milligrams to approximately 120 milligrams for alpha and up to 200 milligrams for beta. The figure on this slide shows an efficiency curve for a gas proportional counting detector using thorium-230 as the source. It is easy to see how rapidly the alpha efficiency decreases as mass increases. It is important to recognize that this type of curve cannot be extrapolated. That is, if sample mass exceeds the high mass end of your calibration curve, you would need to extend the calibration curve to accommodate that sample. Each analysis that is performed may involve different radionuclides. This means different particle energies. It may well be that with your instrument setup, one size does not fit all analyses. You may need to have several different setup and calibration protocols that are written into each radionuclide method to ensure the correct protocol is consistently used. Additionally, it would be good to review ASTM D7282 standard practice, which describes the setup and calibration of newer vintage gas proportional counters and has recommendations on QC checks for the instruments. We've covered a great deal of material in this module. Gas proportional counting is a very versatile method of radioactivity analysis, but it relies on clean and efficient radiochemical separations in order to achieve very low detection limits for radionuclide-specific analyses. This module has provided you with a starting point for the setup and calibration of a gas proportional counting instrument and how the instrument can discriminate between alpha and beta particles. You should be familiar with the terms deadband, crosstalk, discriminator, and pulse height analyzer, and know how they apply to gas proportional counting methods. A thorough review of your instrument manual should be performed before operating the instrument for sample counting or changing any instrument settings.